All right, let's talk about covalent bonding today in more detail. Uh, we sort of introduced covalent bonding uh, last week. We basically had to because of the naming conventions, but we're going to go into more detail today. I'm sure you're overjoyed. Okay, as a reminder, differences between ionic and covalent bonding. Remember, ionic bonds always form between a metal and a non-metal. Covalent bonds usually form between two non-metals. And for our purposes, I'd say always. They always form between two non-metals. Ionic bonds always involve a complete transfer of one or more electrons from one atom to another to form ions. Then the attractive force that holds them together is purely electrostatic. Whereas covalent bonds involve sharing electrons. So what that means is that the two atoms that are involved in the bond, if they're in an ionic relationship, one of them has a stronger attraction for electrons than the others. And with covalent bonds, they're all on the right-hand side, the nonmetals. So they have similar attractiveness to electrons. So their compromise is to share. Ionic compounds do not contain discrete molecules. They are a network of positive and negative ions. Whereas a covalent bond does form discrete molecules, like the water molecule, carbon dioxide molecule, and they behave independently. All right. All ionic compounds are solids at room temperature. Sodium chloride's a solid. Well, sky's the limit. Covalent compounds can either be solid, liquid, or gas. Just like the all but one of the metals is solid at room temperature, except for mercury. And the nonmetals in their atomic state can be solid, liquid, or gas. Same goes for the compounds. Ionic compounds will always be solid at room temperature. There are no exceptions. But covalent compounds can either be liquid, solid, or gas. Another interesting thing about covalent compounds is they usually produce non-conducting aqueous solutions. That is, that's because they don't ionize. In other words, to have a conducting aqueous solution, you've got to have ions present to carry the current through the medium. Whereas molecular compounds can readily dissolve in water, some of them, but they don't do it by forming ions. So they don't conduct electricity. Table salt in water makes a real good conductive solution. Sugar in water, which can be dissolved to massive amounts, still won't conduct electricity. Oops, went too far. All right, that's the official definition. A covalent bond is formed between two atoms that share electrons and attract, maybe not equally, but attract electrons enough so that they can't relinquish their electrons. So here's a view of the hydrogen molecule, right? One of those diatomics. It's a molecule, but it's still an element. It's a diatomic element. And that distinction, I don't think we've made the distinction yet. Compounds of any kind must be two or more. elements. I should say different elements. If you don't have two different elements, you don't have a compound. So we can have a molecule of hydrogen, but it's still an element because both the atoms are identical. So here's what they do. When you form a bond between two atoms that are identical, like these two hydrogen atoms, obviously nobody wins. So the way they form the bond is they share. And they share, since hydrogen only has one electron per atom, they share one electron each. And a bond is always formed between two atoms with two electrons. One bond is two electrons. So if we may write the H2 molecule like this, and that line represents two electrons. So anytime you have a line between two atoms, it's two electrons. For oxygen, we would have two of them. So that means it's sharing four electrons. For nitrogen, it's sharing six electrons. Okay. But they're all molecules. All right. This is known as we did Lewis notation last week, didn't we? Okay, good. Good. Okay, so if we fill in the missing electrons, there are no missing electrons here. They're both in the bond. But with oxygen, we have two lone pairs for each oxygen. And remember, each atom, when they form a bond, especially with the second, third periods, when they form bonds, they try to make that octet. That's the whole theory behind the Lewis structures. So when you're counting for an octet, you look at that atom and say 2, 4, 6, 8. It's as if these two electrons belong to that oxygen. Or 2, 4, 6, 8. Now, we didn't create electrons, we didn't destroy electrons. And as far as the universe goes, there are only valence electrons. There are only 2, 4, 6, 8, 10, 12. There are only 12 valence electrons involved in this bond or in this molecule. So when you count the electrons, we say this one thinks it has two here and two here. This one thinks it has two here and two here. I can't figure another way to say it. If we did the nitrogen, it would simply have a lone pair there and a lone pair there, and we'd have 2, 4, 6, 8, 2, 4, 6, 8 for each atom. All right. So covalent bond is sharing of valence electrons. Remember, the valence electrons are the ones that are available to enter into bonding. They're the only ones that enter into bonding at this stage of our studies. So we can ignore the core electrons and just focus on the valence electrons when we're trying to form molecules or any type of bond. So if we have, say, hydrogen fluoride, right? If we just drew the dot structures for each one like that, and fluorine is a halogen, so how many valence electrons will it have? It's one shy of an octet, isn't it? That's 7. Right? Right? So it has the opportunity to share with hydrogen like that, form a bond. That gives hydrogen its duet and gives fluorine its octet. So it's a 1-to-1 relationship, one hydrogen, one fluorine. Right. All right. I call these lone pairs. They're also called non-bonding electrons. And obviously, they're non-bonding because they're not between the molecules. I mean, between the atoms. So lone pair, non-bonding works either way. Unless you get the crossword puzzle and lone pair won't fit, try non-bonding. Okay. I gave out copies, didn't I? 4, 5, and 6. Okay. So as I said before, this is a single covalent bond, right, between two hydrogen atoms, and it involves 2 electrons. Carbon dioxide has 2 double bonds for each carbon-oxygen bonding. So the number of bonding electrons in this molecule is 2, 4, 6, 8. It's got 8. Now, we didn't draw in the lone pairs, but if we did, all we'd have to do is say like that, that, the non-bonding electrons. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. Well, they think they do. Now, with ionic bonding, you do get a complete transfer. So there's no wishful thinking in an ionic arrangement. Right? Sodium gives up an electron. Now it looks like neon. It has its octet. And chlorine would gain an electron. Now it looks like argon. It has its octet. For real. As ions. But covalent, it's a thought process. Right? I think I have an octet because I'm sharing with this other atom. There's your triple covalent bond between 2 nitrogen atoms. That's why nitrogen is such a stable molecule. In fact, anybody like potato chips? Yeah, everybody likes potato chips. You don't like them when they go stale, do you? No. Most of the time, they don't last that long. But if you keep a bag around for a while, it will go stale. And it's because of oxygen in the atmosphere. Sets up a chemical reaction with some of the fats in the potato chip. Okay, so one way to prevent that, the manufacturers used to incorporate an antioxidant in the mix. But when you put enough antioxidant in your product, it creates some bad health effects. So instead of putting it in the product, they put it in the wrapper. They impregnated the wrapper with it, and that worked. And then, but FDA didn't like that either. So they came up with, well, why don't we just exclude oxygen altogether? So as they're packaging the chips, they blow nitrogen into them, expel all the oxygen, and zip it up before oxygen has a chance to get back in. So now you've got a nitrogen atmosphere in there, and nitrogen is essentially inert. Because that triple bond is so strong, it won't react under normal circumstances. So now we've excluded oxygen, and your chips will stay fresh for months, as long as you don't open the bag. That same concept behind, well, not exactly the same, excluding oxygen from your frozen foods. Does anybody have one of those vacuum sealers? Yeah, they work great. And you just suck all the air out and seal it and stick it in your freezer, and it won't freezer burn. But that's another issue. Moving on. So how many electrons are shared in a double covalent bond? 2 plus 2 is 4, right? 2 lines, 4 electrons. There are the nonmetal atoms have a tendency to form a certain number of covalent bonds. And that helps you when you're trying to write molecules. You don't have to go back and draw your Lewis structure and say, oh my, how many can we get out of this one? You just memorize the number of bonds that they typically prefer, and you can move ahead with it. Like carbon tends to form 4 bonds. And that's because it has 4 valence electrons. And it needs 4 more. So it'll form 4 bonds to get its octet. Oxygen has that arrangement, and it will likely form 2 bonds. Okay. So here, this oxygen forms 2 bonds, that one forms 2 bonds, and that carbon forms 4 bonds. Okay. The halogens, like fluorine, they only need 1 electron, so they form 1 bond. That's it. Typically. Now you can force certain things to happen, but we're talking about as a general rule, they only form 1 bond to complete the octet. Now you can do it several ways, right? Here we formed a double bond with oxygen to give us 2 bonds. But if we call in a molecule like this, water, now it forms 2 bonds, but one of them goes to one hydrogen and one goes to the other hydrogen. Let's see, nitrogen can typically form 3 bonds. So here it formed 3 bonds with one other atom. But it could form those 3 bonds with hydrogens, like that. And that would make ammonia. Okay. So you find a wide variety of nitrogen compounds because they can form these 3 bonds in multiple ways. And carbon even more, because it can form 4 bonds. It could form, I don't know of any carbon atom that forms 4 bonds with one other atom. I've never seen that. But they can form 3 bonds with other atoms. So they could form 3 and 1, or they could form 2 and 2, right? Or they could form 1, 1, and 1, 1. So that's probably why we have so many organic molecules, because they're based on carbon. There's a possibility. So if we did this, we got room for another bond over here. You got room for one over here. Now you got acetylene. C2H2. And every welder knows that one. So how many covalent bonds can oxygen form? 2. Now there's a strange type of covalent bond. Up to this point, we've been sharing. Like this one donates an electron, that one donates an electron to the bond. Okay. There are some molecules that we've deduced will form bonds by one atom donating both electrons. That's called a coordinate covalent bond. If the electrons come from one side and the other one gladly accepts both of them in the bond, then we have a coordinate covalent bond. The problem is, once the bond is formed, you can't tell. You can't measure. There's no way to measure that it's a coordinate covalent bond. You have to deduce it from the reactants. What were their states before? Now, how are they bonded? How did they get there? You have to prove to yourself or to your colleagues that there's no other way for that bond to form except by this coordinate mechanism. That's the only way we can justify this type of bond. So here's an example. Let's see. HOCl is a real molecule. Is it O? Yeah, O's here, and the chlorine's here. So we have an octet there, and we have an octet here. So that's a perfectly happy molecule. If we put it in water, it would be hypochlorous acid. But if oxygen comes along and wants to, let's see. Okay, if oxygen comes along, let's see, oxygen would have that, 1, 2, 3, 4, 5, 6, right? If oxygen comes along and forms a bond, well, this one doesn't need an octet, right? So what we have to deduce is that it goes like that, and the bond forms with those two electrons, right? So the approaching oxygen, the added oxygen, gains an octet, and chlorine doesn't lose an octet, okay? There must be an energetic advantage for a bond to form. In other words, after the bond forms, the whole system has that lower energy. That implies stability. That's where you go with reactions. The more stable it is, the more likely the reaction is to occur. And that's lower energy. But that's an example of a coordinate covalent bond. And this is just your artist's idea. Regular covalent bonds, they share. Coordinate covalents, they steal. Another example. This just makes the point. Once the bond forms, they're indistinguishable from any other covalent bond. The atoms that do this, remember we said oxygen normally forms 2 bonds? Well, in this case, it only formed 1 bond. So that's a deviation from what we would expect. And that's typical for coordinate covalent bonds. That's one of the clues. That in order to get there, it had to deviate from what we expected to do. Nitrous oxide, right, laughing gas, N2O. We add an oxygen to a nitrogen molecule, a diatomic nitrogen molecule. Add an oxygen. That had to be a covalent bond, coordinate covalent bond. That's the only way you can justify the reaction. Carbon monoxide. In this case, oxygen forms. I'm not sure how they got that one to do coordinate covalent. Because carbon only forms 3 bonds here. Oxygen forms 3. So oxygen went up, carbon went down. Okay. When does a coordinate covalent bond form? Both electrons of a shared pair come from one of the 2 atoms. That's definition. All right. If we've done Lewis dot structures for atoms already, you can also write them for molecules. So what we would do is start with a bona fide molecule. In other words, we know it exists. So our example here is sulfur dioxide. And we want to write a Lewis structure for that. The rules are here in subsequent slides. First thing you do is add up how many valence electrons are in that molecule. So oxygen, look where oxygen is. It's in the 6th row from the left. It has 6 valence electrons each. 2 times 6 is 12. So we have 12 valence electrons from oxygen. Sulfur's in the same family, in the same group, so we have 6 more. So we have 18 electrons to position in our Lewis structure. Okay. Now we've got to decide which atom is in the middle, right? should we put one of the oxygens, should we put the sulfur on one end and let the oxygens hang off the right side? Or should we put the sulfur in the middle? If you're not told or shown how to do it, then the best thing to do is say which one is further to the left or below. That would give it a more ionic character. And the first one in a formula is, we learned when we were naming them, is the metal. So sulfur is below oxygen, it would come first, and that would put it in the middle. So we would write sulfur in the middle and then just form one bond on each side. All right, so that's 2, 4. We've used up 4 of them. We have 14 left. Now you start from the outside and work your way in. So we've got 14. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we've got an octet here and here, and we've used up 12. We got 2 more electrons. Then we move in. Those 2 electrons have to go here. Okay, that's what we call a valid Lewis structure. Okay. So there you go. That's what you end up with. Now, instead of writing the pair of electrons, I put lines. I do that so that it's easy to tell what's bonding and what's not bonding. Right? These are bondings, those are non-bondings. Okay. Now, once you've got all your electrons positioned, you try to make an octet for everybody without if you've already got an octet for some of them, you want to make an octet for the ones that don't have it without sacrificing the octet for the other. And that usually means taking a non-bonding pair and moving it into a bonding position. For instance, we could take this pair right here and put it over here. Right? Now you have 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. So we got a double bond on this side. But we could just as easily have written it like this. Right? Taking it from the other side. Those are both valid Lewis dot structures. I misspoke earlier. We hadn't finished. The Lewis dot structure was not finished when I called it valid. This is valid when you set it up like that, where everybody's got an octet. If you can make an octet, fine. That's your goal. But either one of these could be a valid Lewis dot structure. All right. Let's see. We're going to get into this later, I think. So this is one of those when we have a theory or a set of rules that we have to use, and the rules hit a brick wall. In other words, what do? Which one is the right one? Well, they're both right. And there's a way to tell that they're both equivalent in probability. So when that happens, we say they resonate. The truth is somewhere in between the two. You have to introduce resonance to make that work. So that's like I said earlier, maybe in chapter 1 or 2. What do you do when a law or a theory goes kaput? Well, you modify it is one possibility. So this is our modification. Or what? You modify it, or you restrict its application, or you throw it out and start over. Oh, well, there's a fourth one. Everybody remember the fourth one? Turn it into a religion, like Darwinism or global warming right? Then it becomes a religion and it's not science anymore. Okay. So here's some samples that we could work on. Hydrogen and fluorine, well, we've done all of them already. All right, so those aren't good examples. We got our answers here. Those would be valid Lewis dot structures. Fortunately, there's only one way to make these, so you don't have to decide. Okay, now we got some more complicated ones that may give us a challenge. Let's try carbon tetrachloride. Right. So how many valence electrons in carbon? Count from the left. 1, 2, 3, 4. 4. Chlorine is a halogen, so it has 7 each, right? All right, 7 times 4 is 28, plus 4 is 32. So in this one, obviously carbon is in the middle. It's to the left of chlorine. So we put carbon there, and then we position 4 chlorines around that carbon. Now, this is not just busy work. We're going to use this procedure to go the next step to help us learn what is the most likely three-dimensional structure of the molecule. Okay, that's where we're headed. Okay, so we've used up 2, 4, 6, 8. 24 left, right? Well, if we put 6 around each one of these, like that, that would be 24, won't it? Yep, we've used them all up. So that's it. Octet, 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 octet all around. That's the only structure we can make from carbon tetrachloride. Now, why did I name it carbon tetrachloride? Because it's a type 3 naming convention, right? Both nonmetals. So you go straight to the type 3. That means you just say how many there are. 1 carbon and 4 chlorides. Okay? If you're not practicing these things, then I cannot paint a rosy picture for you. How about that? It's like learning a new language. Learn how to name compounds and how to write the formulas from the names. You have to know it. If you don't know it, then your ship is sunk. Okay, total number, we did this one before. The total number here would be 18. Right? Sulfur and oxygen in the same family, they have 6 valence electrons each. 3 times 6 is 18. So remember, some ionic compounds contain polyatomics. Right? We went through that in the naming convention. Polyatomics are covalently bound atoms in a unit that happens to have a charge. Right? So within the polyatomic is covalent, but from the polyatomic to its neighbor is ionic. So here we have potassium sulfate. We know sulfate is a 2- charge, potassium is 1+, so we need 2 of those to balance the charges. This is an ionic situation here between these 2. So when you write the structure, you would separate, put the sulfate in here with its 2- charge, and it would have a potassium on either side. Okay. Then within the polyatomic, that's where you would write the dot structure. Dot structures are only used for covalent compounds. Well, they're used for covalent entities that may be in ionic compounds like this. So how did we get sulfate to be that? SO4 2 minus, right? Sulfur and oxygen in the same group, right? Yep, so they got 6 each. 5 times 6 is 30. But they also have 2 extra electrons distributed over that unit. So we have to add those 2 together. So now we have 32. So if we have sulfur in the middle and oxygen out here, that's 2, 4, 6, 8, 24. Right. 6 electrons now would make an octet for each oxygen, and 4 of those would be 24 electrons. All right, so we've used them up, and you have to put the charge. Otherwise, you're ignoring 2 of the electrons. This has 2 extra electrons than it needs to be neutral, but it also needs them to make all the octets. So the sulfate is that molecule. I mean, this entity, and it goes right in here as shown in the slide. And the authors are making a point of the fact that you don't write it the way on the right-hand side. That would assume that this whole molecule is covalent, but it's not. It's covalent within an ionic. All right, so how many valence electrons did we count up? 32, wasn't it? Yeah, 32. And if you were asked to do this dot structure for one of these polyatomic ions, don't forget to put the charge. Bracket and charge. Okay. Let's see. Doing good on time. Let's do one more polyatomic just for fun before we get into the structure. The geometry of molecules. Let's take nitrate, like that. That's your polyatomic. They're all covalently bound. So we need nitrogen is 5 positions over, so it's 5 electrons. We have 3 times 6 is 18 plus 1. All right, so that's 24, correct? Electrons. Nitrogen's going to be in the middle. So we have 3 oxygens. 2, 4, 6 is 18 left over. 2, 4, 6, 8, 10, 12, 14, 16, 18. Used them all up. Except nitrogen doesn't have an octet yet. So how do you form an octet? Well, you steal a pair from one of the oxygens. So let's say this one, like that. And then you have the charge. But that's only one possibility. We could have done it from this one or from that one. Right? So if we had other Lewis structures to deal with, we could draw them like this. Say we took, I'll tell you what, that's okay, that's okay. We'll do this one and this one, and we'll put the double on this one. Go. And then over here, we'll do another one for the other oxygen. All of them are valid. So guess what we have to do? It's time to resonate. That's how we would represent the nitrate ion. Okay. All right. I said we were headed for molecular geometry by doing this. So once you've got the Lewis dot structure, now we can use another theory, or a model actually, called the valence electron. Let's see. VSEPR, valence shell electron pair repulsion. Okay, so why are we interested in the three-dimensional structure? The reason we're interested in the three-dimensional structure is because it leads to predicting various chemical and physical properties of the molecules. If the molecule is like this, and say oxygen, usually to the right and above, they have a stronger attraction to electrons than their neighbors to the left or below. That's called electronegativity. So the most electronegative atom in the periodic chart is fluorine. And an arbitrary scale that is proposed by Linus Pauling is 4.0. And then way down on the lower left-hand corner, like cesium, would only have like a 0.8, I think. So the higher the number, the more electronegative it is. And that means it pulls stronger on electrons. So oxygen is to the right of nitrogen, and it's going to pull electrons that way, and that way, and this way. Right? So what does that do? Well, it doesn't break the bonds. It just sort of, the electrons spend more time over here than they do over here. So it gives you a slight negative on these oxygens and a slight positive on the nitrogens. That leads to electrostatic attractions among the molecules. Like if you have, you're going to have more of these in solution, then they're going to be attracted to one another simply by this electrostatic difference. Now, these are not complete charges because this is a covalent molecule, but it does give it a slight, what we call polarity. All right, this VSEPR model is based upon the assumption that when we have this structure, all the electrons are going to try to stay as far apart from each other as possible. They're going to stay bonded, of course. If they're in the bond, they'll stay bonded, but they're still going to repel each other. So these bonded electrons are going to push away. These non-bonding electrons are going to push away from each other. And they're going to form the most stable three-dimensional structure possible for minimizing repulsions. So that's why it says valence shell electron pair repulsion. That's the basis for the model. Minimizing those repulsive forces. Okay. So okay. You have to draw the Lewis structure first. Then we can view them in a three-dimensional space. And there are regular shapes that from which we start, right? Like linear or equilateral triangle or tetrahedron. Everybody knows what a tetrahedron is. It's a triangular base pyramid. Tetrahedron. Cubic. Actually, cubic's not a good example. Let's see. 3, 4. We have bipyramidal, trigonal bipyramidal, and we have octahedral. That's as far as we're going in this class. So you only have to learn how to visualize those structures. So we draw the Lewis dot structure. And then we determine the number of electron groups present around the central atom. So we're going to start off with real simple molecules like this, where there's only one central atom. Keeping in mind that large molecules will have several points of symmetry. Like large molecules, you might have one geometric structure at this end of the molecule and a different one at this end. And we count groups. So this is a group, this is a group, and this is a group around that central atom. Even though it's a double bond, we count it as a single group. So when you have three single groups and no lone pairs around this central atom, then you distribute them so that they're equally spaced. And the most efficient way to equally space these is to put them in an equilateral triangle. Like that. Okay, I left out the extra electrons. But when you have three pairs, an equilateral triangle positions these as far apart from each other as possible. So it's a planar trigonal molecule. Now the equilateral triangle is what we visualize here. But that's not the molecule. That's just what we visualize as the three-dimensional structure. The molecule is here with the bonds. So when we look at the bond angles right here, we can say, what's the internal angle for that? Well, how many degrees would you go all the way around? 360, right? Right. So a third of 360 is 120. So each one of these bond angles is 120 degrees. Ideally. Then you get into, and we're not going to go too far with this, but you get into saying, all right, you got this single, actually, these bond angles can be measured. And for this particular molecule, they are all 120 degrees. So that means we don't actually have a double bond over here. All the bonds are equal. Okay, so they're not single and they're not double. They're somewhere in between. That's just one of the lines of evidence that we use to determine that this resonance idea is not reality. It's just the fix that we added to our theory so that we could draw the structure in Lewis format. But actually, it should be drawn like this. Yeah. But the Lewis structure doesn't allow for partial bonds. But it's like I always say, nature just does what it does. And we're trying to develop rules and theories to explain it. This is reality, right? Our explanation for this theory is to do that. All right. So once we've decided the number of electron groups, then we go to the molecular geometry that will accommodate that number of groups. And if we had a lone pair here, let's take ammonia. Right? We drew ammonia earlier, like this, and it had an unbonded pair there. So around that central atom, how many groups do we have? We have 4, right? 3 bonded, 1 non-bonded. So 4 is the best regular arrangement for 4 is a tetrahedron. Right? You have a triangular base. Let's say maybe like this, that, and then you have your nitrogen in the middle, and your hydrogens here, here, and the lone pair up here. So we would draw our tetrahedron here, there, down here, like that. You have to visualize it in 3 dimensions. But the bonds themselves are between here and here, here and here, here and here. So the tetrahedron would put the lone pair up here and these hydrogens on this triangle at the base. But there's one thing about lone pairs. They're not confined by another atom into a bonding space. So what they tend to do is they balloon. There's nothing holding them back. So when they balloon like that, they put pressure on these bonds and they force these other hydrogen atoms to be pushed down and closer together to avoid the electrostatic interaction with that lone pair. All right. Let me erase this. I'm going to try to build a table. So hopefully it'll make more sense how to use the Lewis dot structures and translate them into a three-dimensional structure. So in this column, I'm going to have electron groups, numbers of electron groups. And in this one, we're going to have, let's see, electronic geometry. Right? So our electronic geometry in ammonia was tetrahedral. But if you actually look at the molecule, you're not going to see the lone pair of electrons. You're just going to see the atoms. So what does that lead to in terms of the molecular geometry? Okay. So if we have one group, right, that's obvious, like we had A bound to B, it's got to be linear. There's no other option. If we have two groups, like B, A, and B, like that, two groups, that has to be linear also. Even if B is a lone pair, it would still be linear. Okay. If we have three groups, right, like let's see, A and then B, 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 this would be trigonal planar. Another way of saying that is an equilateral triangle. Now, the molecular geometry would be that if all of these positions were occupied by atoms. But if that one happened to be a lone pair with three and like this, one or two lone pairs, it doesn't matter. Well, in this case, it would just be one, right? Because we're substituting for that one. Then this would still be trigonal planar electronic, but this would be bent. Or your book might call it angular. That's a bent molecule. If we have four, right, we have like A in the middle, and then four groups around it, then this would be tetrahedral. And of course, this would also be tetrahedral. But if one of those was a lone pair, so we had a lone pair up here, like our ammonia molecule. Now we've got pressure on these at the base, and we would expect, well, it's going to be tetrahedral electronic still, but those would be on the base, and we would expect it to be trigonal planar, but it's not because of the pressure here. What we have now is a trigonal pyramid. That If we had two lone pairs, now I'm running out of room. If we had two lone pairs here, and then we still have the B here and the B here. Now with this tetrahedral electronic, we're going to have another bent molecule. Now I didn't give you any examples here. I probably should have. Examples here for this one would be like boron trihydride. I can't think of one for that one right off the hand. This one would be carbon tetrachloride would be a good one. This one would be ammonia, would be a good example. Example of this one would be water. Water would be a bent molecule. That's why water is so polar. One of the reasons water is polar. Okay, let's see. I've still got some more to go. So let's see. Electron groups, electronic geometry, and molecular geometry. Okay, so we have 5 electron groups. Well, now we've got one in the middle. So we got our A in the middle. And we've got 5 other atoms positioned around it. Well, I drew them in the wrong place and give myself space. Let's do this. Just move it over. Electronic geometry and molecular geometry. Okay. So now the most efficient way to arrange those atoms is in a trigonal bipyramid. And it would look something like you'd have a trigonal base for a pyramid, but you'd have a B here, B here, B here. Then you would have a B up here and a B down here with A in the middle. And so you would form like that. Okay. Can you visualize that? Maybe you need a model. So this would still be a trigonal bipyramid. And all along, we're just trying to minimize repulsions. This is the most stable. Now, when I give you this information, all of these have been verified with real molecules. Right? So let me see, what would be a good example here? 1, 2, 3, 4, 5. Let me see if we got some examples. Maybe I'm beating my head too hard. We might have to come back to those just as examples. Here we go. So there's the electron pairs and examples. Well, these are just models. They don't tell us the molecules. But they do give you a three-dimensional visualization. We're down to the 5, the trigonal bipyramid. I thought I had some examples in here. Molecules. Hold on. No, I don't. Well, that's okay. If one of these is missing, which one goes missing? Well, logic would say these B's up here and there are further away, right? We would expect them to be where the lone pairs would reside. But in fact, the lone pair resides on the triangle. So if you got, still got 5, but you have here, you got a lone pair up here, and then you have these other 4. Now, it's like that. So in order to visualize this one, remember the bond's there, the bond's there, bond's here, and bond's here. If you turn this thing on its side, you have these 2 struts, and you have the other 2 B's down here and 2 B's out here. It's a seesaw. Looks like a seesaw. Okay. And if you have another lone pair, two lone pairs, and then you only have three Bs, then the second lone pair also goes here. Now, if you turn it on its side, it looks like a T. So that's a T shape. And finally, if you only have A and you have three lone pairs and two Bs, you have linear geometric structure. Because now you have three lone pairs around the triangle and it's a linear structure. Okay. Let's see. I might have to go over here and erase some things to make room for 6. 6 is the last one. That's as far as we're going. People that do this for a living, I mean, they just eat, drink, and sleep this stuff. So if we have 6 electron groups, then we have something like A in the middle, and then 1, 2, 3, 4, 5, 6, like that, like that, like that. The electronic structure here is going to be octahedral. So you have a square in the middle, like that, that. And then you have a B up here and a B down here, and a B at each point here. And then your A's in the middle, right? So you form these bonds here and here. That. So how many, if you draw connectors with all these and you turn it on its side, you get this arrangement here, and you can see how many sides does it have, right? 3-dimensionals are always hedrons of some kind, right? Tetrahedron or octahedron would have 8 sides, right? So if you draw that structure connecting all the atoms, then you notice you've got 4 on top and 4 on the bottom. There's your octahedron. So that's with 6. And of course, that's the molecular structure also, if every position is occupied by an atom. Now, if we, let's see, do we do it? This is okay, there's the trigonal bipyramid. There's the tetrahedron on the left, the trigonal bipyramid on the right that goes through the seesaw, the T-shape, the linear. We did that one on the board. And then, oh, they don't do any more octahedrons. So if we were missing one of these, where would it go? Now, it's where we would expect it. One lone pair would be there. Okay. So if that's the case, with 6 and 1 lone pair, let's see, BA. Like that. 1 lone pair, that's a square base. If you turn it upside down, that's a square base pyramid. You know, just like the pyramids of Giza. Square pyramid. Okay. If we're missing 2 here, they're also at the apex. So we would have 2 down there. Now you've got just square planar. Okay. I think that's far enough. I mean, you can miss some here, then you start missing some on the outer arrangement. And in that case, you have a T shape with 1 more here and 1 more here would give you a bent molecule. It's logical progression from there on. Okay. So what does that mean for physical and chemical behavior? Well, if you have a completely balanced molecule, say all the B's are the same, and you have this central atom A, and they're positioned at their, and say these Bs are more electronegative than A, so they're pulling electron density away from A. From the outside, the molecule looks like it's nonpolar, right? All these bond polarities cancel one another out. So that means the molecule is going to behave as if it's nonpolar. It doesn't have any odd distribution of electron density when it approaches another molecule. And so they just behave as if they're billiard balls. But if we have something like water that's bent, and hydrogen is more electronegative oxygen is more electronegative than hydrogen, and we get the electrons moving that way, plus these lone pairs, then you get a huge negative side and difference with positive sides. I use that little, that's a Greek delta. It means small. Small difference in charge. Now, when you get water molecules approaching one another, the negative side is going to approach this side, the positive sides will approach the negative side, and you'll get a polar attraction. Right? That's why water is liquid at 1 atmosphere pressure and normal temperatures, like 20, 25 degrees Celsius. And we have liquid water on the surface of the earth. Right? If it were not polar like that, say if it were linear, then we'd be in big trouble. Because under those circumstances, water would just evaporate. It'd be all gas. And over a billion years or so, it'd just all be gone into space. And this would be a dry hulk with no life. So I'm thankful for bond polarity. All right, let's see if we can determine the shape of these. Everybody get that? Okay. It's been recorded. All right. Now, if you want to know how far I'm going to carry this concept for this class, since this is an introductory class, I'm not carrying it very far. And the best way to know how far I'm carrying it is to work problems in the review document. And that'll tell you just how serious we want to get, or how far we want to carry this concept. I think for this course, basically what we want to do is try to understand how molecules attract one another. So let's see, HCN. So we would start with that, and we would say, how many valence electrons? All right, 1, 4, 5. All right, so we have 10 electrons. Carbon's in the middle. Hydrogen can't be in the middle, right? Because it can only form one bond. And then nitrogen. So that's 2, 4, minus 4. We have 6 electrons left. So hydrogen can't take any more because it has its duet. So we put all those 6 around nitrogen. Okay, now we've used them all up. Now we need to make an octet. How do we make an octet? We can't work from hydrogen side because it's exhausted. So we take this one, and make another bond there and there. Now these are gone. These are gone. Right. And we have 2, 4, 6, 8, 2, 4, 6, 8. That's hydrogen cyanide. Every murderer's favorite chemical. So there's our Lewis dot structure. All right, what does that say about the geometry of this molecule? Well, this one, when you've only got 3 atoms, there's just one center. There's your center right there. So how many groups around that center? You have 2 groups. Both of them are occupied by atoms. They're bonding. So two groups means linear. That molecule is linear. Okay. Now, what does it say about its polarity? Well, okay, the question is bond angles. So what's the bond angle of a linear? Well, the bond angle, in order to have a bond angle, you have to have three atoms. So the bond angle would be this at the apex, and then we would go like that. 180 degrees. That's linear. Okay. A word about polarity. Nitrogen is more polar than carbon. And carbon's about the same as hydrogen. So we're going to get a molecule that's slightly polar that way. And I draw this line to show you this is the positive end and this is the negative end. That's what that means. So our molecule is going to say, all right, this side is going to be slightly negative. This side is going to be slightly positive. And that's the way they approach each other. Right? In gaseous form, probably. They approach each other and they would align so that this end would be aligned with that end of the other molecule. Let's see. So that's linear. Ammonia, ammonia starts out with 4, right? Like that. 1, 2, 3, 4, 5. 1, 2, 3, 3. And then 2, 4, 6, 8, and 2, 2, 2. So with 3 groups, actually 4, your electronic structure is tetrahedral. But when you just, the way I do it is I draw the tetrahedron, put everything in its place, and then cover up the lone pairs and say, what do I got left? Now we have a trigonal pyramid. Well, initially, the bond angle for a tetrahedron is 109.5 degrees. If this were carbon and there were all hydrogens, then the bond angles would be exactly 109.5 degrees. But with this lone pair out there doing its ballooning thing, and it's putting pressure on the other bonds, it pushes them together to where the bond angle is 107 degrees. It squeezes them. That's what lone pairs do in a molecule. O3, what's O3? You ever seen that one before? It's ozone. That's the molecule that's up in the stratosphere that absorbs the more dangerous or lots of the ultraviolet from the sun and protects us on the ground. And in the Arctic regions, from time to time, we get these big spaces over the Arctic that are depleted in ozone, called the ozone hole. And various reasons they've given, of course, the environmental bugs are going to blame it on some pollutant. And there's chemical evidence for that too. The hydrofluorocarbons, freons, right, that get expelled in there, they eventually reach up there in the top and they catalyze the breakdown of ozone. All right. So I mentioned electronegativity kind of ahead of things. And this is a periodic trend in the table. There are several periodic trends in the table, and we're not going to go into, I don't think we go into all of them, simply because this is an introductory course. But electronegativity is a useful trend to be of which to be aware. Yeah, it helps us with understanding polarity in molecules. The general trend, and I mentioned this earlier actually, the general trend in the periodic table for electronegativity is from lower left to upper right, electronegativity increases. So as you go up in a group, electronegativity will increase. And as you go from left to right in a period, it will increase. So lower left, upper right. So what we would expect is fluorine to be more electronegative than oxygen, and oxygen to be more electronegative than nitrogen. So when they're in bonds, you can say, all right, the polarity is going to shift a certain way based on their attractiveness for electrons. They're still shared electrons. They just sort of share unevenly. And here's an idea of a trend. I guessed right. Rubidium's 0.8. I think cesium is about 0.8 also, down the lower left-hand corner. Now notice that the transition metals are missing. Transition metals don't behave very well because they have those. We cover we did electron configurations. We did that, didn't we? I think we did. We're filling d orbitals in the middle. And d orbitals can hold 10 electrons, right? So that blows the octet out of the water. So we focus on these trends with the representative elements, right? The first two, alkaline metals, alkaline earths, and then the last six, right? Boron, carbon, pnictogens, chalcogens, and halogens. And the trend is generally from lower left to upper right. All right. What's the general trend for electronegativity? Lower left, upper right. So what's the explanation for it, though? Well, if you go from left to right in a period, you get an increasing number of protons. And that means a stronger nuclear charge is pulling on those electrons. So we call that an effective nuclear charge. And the electrons that are being added along with the protons, as we go from left to right, and the atoms from the elements from left to right, those electrons are going into the same principal quantum shell, right? So they're not closer to and they're not farther away in general from the nucleus. So as you add that extra proton, it tends to pull harder on those electrons. It actually shrinks the atom. So there's another trend, atomic size decreases from left to right because of that force, but it also increases electronegativity. And then from top to bottom or from bottom to top, what you see is an increasing size, right? Each time you move down in a period, from one period to the next, you're adding a principal quantum number shell. So it's getting bigger. And what you're doing is you're adding electrons, you're adding protons in the nucleus, but you're adding electrons out here further away from the nucleus. And there are electrons, those are the valence electrons. And the electrons that are left over that you added on top of are the core electrons. And what they tend to do is that negative charge shields the nucleus. Right? It tends to balance some of that positive charge. So as you go from top to bottom, you decrease electronegativity because you're adding to the shells, adding more electrons to the shells, and you're getting shielding on the inside from those core electrons. So what happens is you reduce the effective nuclear charge. Even though you're adding more protons, you're shielding all that added positive charge by the core electrons. So put those two together and you get lower left to upper right. Okay, so if lithium and fluorine react, which element will have more attraction for the electrons? Well, lithium's on the far left and fluorine's on the far right, so fluorine obviously will have the greater attraction. Right? And the bond between fluorine and iodine would be slightly polar also. You know that halogens can bond with their neighbors. Right? You can get fluorine and chlorine, fluorine and iodine, bromine and iodine. You can get those molecules formed. And the electronegativity of fluorine is greater than iodine, so it's going to be polar toward fluorine. simply because of the trend in the group. So which of these has the higher electronegativity? Well, let's see. You can discount noble gases because they're perfectly happy. They've got all the electrons they need, and whatever positive charge they have in the nucleus is being shielded. They don't even count. They are the lowest electronegativity. Now we can choose between, let's go hydrogen, let's go oxygen and chlorine. Oxygen is above chlorine in the table. So oxygen should be more electronegative than chlorine. Hydrogen is kind of off by itself, and it's only got one proton anyway, so it's not the most electronegative. I think oxygen should be the most electronegative. And then we can go back to our table, right, and say, okay, oxygen is 3.5, chlorine is 3, hydrogen is 2.1, and that's a little less than carbon. It's closer to boron. Okay. So that verifies it with actual numbers. But we deduced it fairly confidently that oxygen was the more electronegative of all in that group. So what I've been demonstrating with that arrow and a plus sign on the end of it is bond polarity. It just shows you which direction the electrons are pulled and gives you the positive side left behind, the negative side where the electrons move, slight difference in charge. Now, the greater the difference between electronegativities, the greater the polarity of the bond. Right? So lithium and fluorine, actually, that would not just be a polar bond, that would be an ionic bond. So if we got something closer to home, say carbon and fluorine, that would be fairly polar. It would be more polar than a nitrogen fluorine, and that would be more polar than an oxygen fluorine bond. So these non-polar covalent bonds, to be absolutely non-polar and still covalent, would be between two atoms. It wouldn't be a compound necessarily, but you can guarantee a non-polar bond between two of the same elements. Okay, like hydrogen, like nitrogen, like oxygen, like any of the diatomics up there would be examples. Whereas if we form one between hydrogen, which is 2.1, and chlorine, which is, what was it? 2.8, something like that. The difference between the two, the higher that difference in the the electronegativities, the more polar the bond. So this one turns out to be a polar covalent bond. Right? And that's the way we represent them, either with the delta plus, delta minus, or with that arrow with a positive tail. Now, here are the general rules. This just tries to help us classify things. If you subtract the two polarities, the two electronegativities, and you get something less than 0.4, then you're pretty confident it's a nonpolar covalent bond. If it's between 0.4 and 1.5, then you can be confident that the bond is polar, but still covalent. Now, if it's greater than 2, it's definitely ionic. But if it's between 1.5 and 2, it depends. If it's a metal and a non-metal, we call that region ionic. If it's between two nonmetals, we call that still polar covalent. Okay. Let's see. Am I running out of time? 10:30? Oh, I got till 11, don't I? Okay. I think we can finish. Yeah, I'll try to pick it up. So if we arrange these following bonds in descending order of polarity, in other words, the most polar to the least polar. The nice thing about A is we've got different molecules attached to the same atom and carbon. Okay. So the most polar is going to be the one where they're further apart from each other in the table. Carbon and fluorine would be the furthest apart, wouldn't they? So carbon and fluorine, let's see, from greatest to least. So that's the most polar. And the least polar would be oxygen and fluorine, because they're right next door to each other. That leaves nitrogen and fluorine in the middle. So carbon, nitrogen, oxygen in that order. Now the next one is a little more difficult because we've got different elements bound together. So we got carbon and fluorine again. We got nitrogen and oxygen and silicon and fluorine, correct? Okay. So for this one, we look at the distance between the two atoms. Carbon and fluorine is like 3 positions away. Nitrogen and oxygen are right next door. Silicon and fluorine are pretty far apart. So nitrogen and oxygen should be the least. Right? And the greatest would be the furthest apart. Silicon and fluorine are farther apart than any of the others. And that leaves nitrogen and oxygen in the middle, right? Wait a minute. What am I doing? No, carbon and fluorine in the middle. There we go. Let's see if I got it right. Silicon, carbon, nitrogen. Yep. From greatest polar bond to least polar bond. And the last one is 2 chlorines, a boron and a chlorine, and a sulfur and a chlorine. Okay. So this one's going to be the least polar. It's going to be nonpolar, actually. And then boron and sulfur. Boron, sulfur relative to chlorine. Sulfur is closer to chlorine than boron is. So I would put it next here. And then boron and chlorine first, as far as polarity of the bonds go. Okay. Now, if you don't have the chart to look at, that's the way you would rationalize it. If you have the chart, then all you have to do is just compare the numbers. All right. Which of the following bonds would be the least polar yet still be considered polar covalent? Okay, have to be covalent. So that means we would eliminate the metals and the nonmetals. Right? Magnesium and oxygen are out. Silicon is pretty close. So it would be more polar than any of the others. Oxygen is not polar at all, so it goes out too. So magnesium, oxygen, silicon are out. We compare carbon and nitrogen to be the least polar. The least polar. Carbon, nitrogen is right next door to oxygen, so I'd say that'd be the least polar, wouldn't you? Right, we cross those out. Those are the closest together in the periodic table. How about the most polar without being considered ionic? Well, in that case, of course, we'd have to throw out magnesium. We have to throw that one out because it's nonpolar. We throw that one out because it's ionic. And then we'd say the most polar would be the furthest apart. So silicon and oxygen, maybe? Yeah. I would say those would be the most polar. That'd be the most polar bond. Now, we've talked about polar bonds. How does that fit into the decision of whether a molecule is polar or not? You need consider two things. What is bond polarity? Right? If you have a molecule that has nonpolar bonds in it, then the molecule is nonpolar. Doesn't matter what else you do to it. If they're all equally nonpolar, then the molecule is nonpolar. But if you have polar bonds, then you have to consider the geometry. That's why we went to all that trouble with the VSEPR model to determine the geometry. Because now, once you find the polarity of the bonds, do they reinforce each other or do they cancel each other out? In the case of methane, that's a tetrahedral molecule, and all the bonds would be, actually, they're not that polar. Let's try another example. Carbon tetrachloride would be a better example. Carbon tetrachloride is polar toward the chlorines, but they're positioned equally around that tetrahedron, and they cancel each other out. So carbon tetrachloride is a nonpolar molecule. Not based upon this, but based upon that. Their bonds are polar, but the geometry cancels all the bonds out. You ever heard of a concept called vector math? Vector math takes into account not just the number, the magnitude, but the direction. It's a common concept in physics. Does anybody have physics? No physics? Okay. Well, if you do, that's one of the first things you'll do is draw vector diagrams. So that probably scares most of you away, right? Okay. Those are the two concepts you need to determine the polarity of a molecule. Here we have carbon dioxide. We've determined it's a linear molecule and the bonds are polar toward oxygens, but they're equal in magnitude and opposite in direction. So carbon dioxide is a nonpolar molecule. Okay. That's why carbon dioxide is used in supercritical fluid extractors. I used to have one. We operated it with the USDA. It's very nice. You compress the gas until it turns into a supercritical fluid. That just means that it behaves like a fluid, and you can't tell whether it's a gas or a liquid. But they're extremely effective at penetrating the cell walls of our plant materials that we wanted to extracting materials, bringing them out of the cell, and then all we have to do to recover the extract is let off the pressure. And carbon dioxide's gone, and we got our extract right there. And it doesn't damage it, right? It doesn't damage the molecules that we're interested in. Other extraction procedures like socklet extraction, where you have reflux, methanol refluxing for hours, right? That added heat will damage a lot of molecules. So this supercritical fluid extraction is very nice, and it's because carbon dioxide is a nonpolar molecule that it works so well. Okay, I mentioned water before, right? It's a bent molecule. The bonds are polar, but they're offset from one another, so they reinforce. And when to demonstrate that vector concept, right, if we have something like this and like that, they're not canceling each other, but they're actually vector addition to each other. And that makes the overall molecule polar in that direction. Oh, we did hydrogen cyanide earlier, right? So the bonds are polar toward carbon from hydrogen and nitrogen from carbon, they add together to make the molecule polar on the nitrogen side, nonpolar on the hydrogen side. Okay, silicon dioxide, does it contain polar bonds? More than likely, silicon and oxygen are far enough apart. So is the molecule polar or nonpolar? All right, so if we do silicon dioxide and work out the geometry, right? First thing we have to do, we have, let's see, silicon is 4, and 2 times 6 is 12, so we have 16 electrons. We put silicon in the middle, oxygen, oxygen, 2, 4, minus 4, so we have 12 left over, 2, 4, 6, 8, 10, 12. Okay. So we want silicon to have an octet. We move these two and these two for balance. There's another reason for that, but we're not going to get into it because it requires too much time to learn how to calculate the formal charge. But that's a valid Lewis-Dot structure. Well, the bond may be polar, right, toward the oxygen. But this is a linear molecule, right? It's got 2 groups, so it's linear. And those, they cancel each other out. Oh, they're relying on me to explain it. So there you go. Which of the following molecules are polar? Well, if you're in the middle of a test and you're trying to answer a question like this, look at the question. If it says, which of the molecules are polar? Look at your choices, which are absolutely not polar. The ones where you're bound between two, the same element, like fluorine is nonpolar, right? Throw it out. Carbon tetrachloride, we know that one from past experience is a tetrahedron. It's equally spaced, right? All the polar bonds cancel one another out, throw it out. HF is a linear molecule, right? With fluorine, the most electronegative, that one has to be polar, right? Ammonia, we drew that one before. It's a tetrahedral structure in terms of its electronic structure, but cover up the lone pair and you got a trigonal pyramid, right? With nitrogen more polar, more electronegative than hydrogens, so it's going to be polar toward the nitrogen side, right? So we've got 2 already, HF and NH3. How about SO2? We just did SO2. It's nonpolar. So the only 2 polar ones should be HF and ammonia. Oops, wait a minute. Did I do that one right? SO2? Oh, no, I did silicon. Excuse me, silicon. SO2 is, we drew that one earlier, didn't we? SO2? And let's see, what is it, 18? 18, 2, 4, 6, 8, 10, 12, 14, 16. We have 2. Okay, so that's a bent molecule. Now, oxygen is more electronegative than sulfur, so it's going to be pulling this way, but the molecule is bent. Right? It has these over here, it has that like that and that. So this polarity is going to drive it that direction. So yeah, right, sulfur dioxide is polar. All right, let me see how much time we got to mess with this. I'm gonna have to skip these. Water is polar, the rest of them are not. Binary molecular compounds. We discussed this in naming compounds. Molecular compounds are always formed between two nonmetals. The binary compounds, two nonmetals. And we know how to name them because they're type 3 compounds. And we just need to know the numerical prefixes. Right? So carbon dioxide is correct. Sulfur hexafluoride, dinitrogen tetroxide, those are all type 3 compounds for naming conventions. And there are your prefixes again. I think I put these in chapter 4 too, didn't I? Those prefixes. I think I did. Those are examples. Some have accepted common names, and these are inherited from antiquity, right? Water, obviously. Hydrogen peroxide, ammonia, hydrazine, right? Everybody knows hydrazine from World War II. Right? The Germans put them in their rockets and their little rocket plane, and they killed a bunch of technicians on the ground before the plane got in the air because it's such a toxic material. Methane, CH4, ethane, nitrous oxide, right? Dinitrogen monoxide would be the systematic name. Nitrous oxide, or otherwise known as laughing gas, is N2O, and NO is nitric oxide. That's the one that you see advertised. Super beets will increase your nitric oxide and cause your vessels to dilate and decrease your blood pressure. Nobody's heard that one? Oh. I know. While I'm listening to these commercials, you're at home studying, aren't you? So which of these is named incorrectly? Nitrogen dioxide is correct. Phosphorus pentoxide is not correct. It's diphosphorus. There are two of them, diphosphorus pentoxide. And you've got the extra credit, 50 ways to name your compound. That give you practice plus get some more points. Sulfur trioxide is true. Iodine monochloride. Those are all true. The only one that's wrong is P2O5. If you look on the, does anybody ever read labels? I asked you this before, didn't I? Nobody in here reads labels. If you read the labels on a fertilizer bag, what do you see? See 3 numbers, right? Like if you buy it from the store for your potted plants, it might say 10, 10, 10. Well, the first number is nitrogen, 10% nitrogen in that product. Second one is phosphorus, but it's not phosphorus percent, it's P2O5%, that compound. And then the last one is potassium, and it's not potassium percent, it's K2O%. And this is from years gone by from analytical chemistry. When they were analyzing fertilizers for phosphorus, the product that they got out of the analysis was P2O5. So they just left it that way. Okay, concept questions. We got 6 minutes. So an unknown is thought to be an aqueous salt solution. However, it was determined not to be a conductor of electric current. Aha. So we know it's covalent. Definitely. Through analysis, it's found that the unknown contains carbon, hydrogen, and chlorine. Carbon, hydrogen, and chlorine in that ratio, 1:1:3. That's your empirical formula. We haven't done that yet, have we, in this class? That's coming later, I think. Maybe in the next chapter. Yep, next chapter. Which one of the following represents the Lewis structure, molecular geometry, and classification of the unknown? Okay. Well, if we look at the ratio, we need 1 carbon, 1 hydrogen, 3 chlorines. 1 carbon, 1 hydrogen, 3 chlorines. They're all the same as far as the atoms go. Now, which ones actually obey the rules? Well, look down at C. They've got an octet around hydrogen, right? I don't think so. Then we can throw that one out. How about the chlorines? Well, the A and B both don't have octets around the chlorines. Throw them out. What are you left with? D, right? Check it out. Octet around the chlorines, octet around carbon, duets around hydrogen. So with 4 groups around that central atom, it's got to be tetrahedral. And it's a covalent compound. Right, there you go. That one was simple. I still got 4 minutes. Concept question 2. Liquid molecular compound is given to you and you're told to handle it with caution. Okay. It can cause damage or death if it is consumed in large quantities. If it enters your lungs, if you hit with a frozen chunk of this material or if a hot solution of it is spilled on you. However, this liquid is necessary to sustain life. I think I know where we're going with this. And you look at the answers too. The liquid is pure molecular compound, okay? Has no taste, is known to contain hydrogen and oxygen. Identify the liquid, its molecular geometry. All right, hydrogen and oxygen and all that other stuff says it's got to be water, right? And we know water, we've drawn the structure, it's an angular or bent molecule, which means it's polar. Oops, here we go.